Okay, hello, welcome back to day number 2 of our marathon Oracle weekend. That is a marathon, let me tell you. So today there's no more entity relationship diagramming stuff. You're glad to know that we are all done with entity relationship diagramming. And so today is all about SQL. But I'll save you the torture till after lunch. So we'll start, because SQL is about, normally when I teach it for the weekday classes, it's about 3 weeks. 2-3 weeks. So we can cover 2 or 3 weeks after lunch. So we'll cover a couple weeks before lunch and a couple weeks after lunch. Each weekend is like about 5 weeks or so. 5, 10, 15. Yeah, it's about 5 weeks. But I'm putting a little bit more into the first 2 weekends, so the third weekend's a little lighter weight because of the final exam. So we're really doing about 6 or 7 weeks of material. If it seems long and kind of boring, it's because it's 7 weeks of material over 16 hours that you're sitting here. But actually yesterday wasn't too bad. We got out a little bit early. It was okay. I'm going to try and hopefully keep the same schedule today. So we'll break at, we'll have a lunch break and then we'll come back. And then the afternoon is all about SQL. In the morning I'll be talking about database objects and other things. And I've decided the game plan, I would love to show you Oracle actually. And I can't do it today though. So the game plan is I'm putting together my own server. Yeah, I have an old book. Last night I went to my garage actually and I looked at it and I have networking cards. I actually have enough equipment to assemble a small-time server that I'm going to donate to ITU actually. And then I'm going to put Apache on there. It's going to be a Linux server, probably Red Hat. And I'm going to put Oracle on there, and I'm going to make student login accounts, and I'm just going to hook it up. Probably, well, they gave me a little office space. I'll stick it in my office. So that's the goal. We'll see how close I get to it, but I'm going to put together a CS server for ITU, homemade, homebrewed, and just leave it on 24 hours a day, 7 days a week, and put C++ on there, put Oracle, Apache, make it put together a web interface for it, because I'm not like so hip on this whole Amazon cloud stuff. And I went and I looked at that first, and I decided that it's more trouble than it's worth to get Oracle installed, and plus they also charge you. They charge you for the bandwidth and they charge you for the usage, like per minute or per day or something like that. It's just ridiculous. So I'm thinking what we need is just an old-fashioned CS server. So if I get that ready to go and I get that assembled, then you don't have to install Oracle on your computers. You'll have accounts where you log in. And I'm going to talk about accounts today. I'll just set up some generic student accounts, and then you'll be able to log in with those accounts and use Oracle without having to install it on your computer, because that's really not such a good idea. And it's nice for learning. It's good to go through the install, but you don't want to keep it running on your system for various reasons. But it's not meant to be a client. You're not meant to load a client and a server on a client machine. It just doesn't run efficiently that way. So anyway, no promises, but that would happen July 27th and 28th weekend. That's the game plan. And if I can do that, then what I can do then is have exercises for you to do. So you can create tables, and you can drop tables, and you can populate tables with information. And we can actually have a little bit more interaction in this class. We'll make it a little bit more interesting. So I'm looking forward actually to the 27th, 28th weekend when we come back for weekend number 2. I'm probably about 90%, 95% positive I can probably get it working and get what I want by then. It gives me a whole month. I should be able to put it together. And plus I'm using my own resources, so it's not like I have to wait for ITU to budget something. So. And it's just old computer systems. You know, computers these days are a dime a dozen. I could probably go out and buy a brand new one for like a couple $100 to do this with. You know, those big old desktop PCs, you know what I'm talking about. Yeah, they're a dime a dozen used on the internet. Actually, on Craigslist, there's 1 million servers I could buy pre-made already. So I'm pretty confident I'm going to get this together. That would be happening July 27th and 28th weekend, so then I have to prepare some online exercises for you so you can log in and do some stuff. So that's the goal, which is actually good planning because I needed to cover entity relationship diagramming and I need to cover SQL, so we get it all done this weekend. So normally I would wait for SQL for the second weekend, but I'm going to bump it this weekend, so the next time we'll have a little bit more activities going on. And it's better, it's easier when you're doing something versus just listening to me. Plus, it's hard for me to talk all day for 8 hours, so it's easier for me if you guys are doing something as well. So it's a win-win all the way around. All right, so if you just came in, the lectures themselves from yesterday, all 5 of them, are loaded on the website for bhacker.com. I made a playlist. I'm still making more lists and organizing my system. But they're on YouTube. They're also accessible here. They have yesterday's date on it, actually. And so today we'll continue with lecture 6 and on to the end. So if you missed anything from yesterday, or if you don't understand entity relationship diagramming, you can listen to it one more time or so. You also, if you were here yesterday, were familiar with the fact that you could probably do the first 2 assignments already quite easily. So you can knock those out. If you get bored while listening to me today, you can knock those out, put them up into the EMS. I don't know if anyone's done it yet, but we'll see. So we're going to start in now with a guide to Oracle. So it's probably not a bad idea, at least on day 2, to look at Oracle features and stuff. And talking about client-server databases and Oracle relational database. So we'll start out by giving you a little background on the concept. I gave you this background yesterday. This background was with the file-based data processing and the differences between a file-based system and a database system. This was our Database 101 lecture we spent the morning talking about and looking at. In this configuration, each application has its own data files that correspond to its own application. So what we're really, and I'm going to kind of go through this fast because it's sort of a review from yesterday. What we're really looking at are the problems with file-based processing, and the fact that we have that duplicate data, and the fact that we have inconsistency that might exist between the data. So what we end up with is that we don't want to have a database to replace the file-based system and then introduce these problems all over again, which is why we spent some time yesterday looking at the design of the database and using entity relationship diagramming, because really it makes no sense to put together this nice database and then introduce duplicate data and then introduce inconsistencies between the tables and stuff. What we don't want, and it sounds kind of, well, it's kind of like bare bone kind of thinking or minimalist kind of thinking. We don't want the same piece of data stored more than once. If we have the customer's first name, we don't want it again or again and again and again, which is the exact opposite of business people. Business people want multiple copies of everything. They save everything. They want multiple copies. They want reoccurrence of it because, what happens if we lose a copy? Or what happens if we need it? People, even in their personal life, I'm sure, the government says you need to save all your tax stuff for 5 years. I have everything dated back probably about 20 years. And that was also in my garage when I was looking at it. I'm like, what do I need all this stuff for? In fact, I have final exam papers from back in 1990-something from students from like the first time I've taught, like way back in the beginning of time. I'm like, what do I need all that stuff for? But don't think like that in databases. In terms of data processing, we put the database out on a server. So what we're going to do is have one of these, and then all of the application interfaces have the same data to the central database. So this is why the client-server environment lends itself quite well to this. We put it out on a server. We create a database management system to get to it. And then we have all of these things that connect to it. Checking account programs, savings account programs, auto loan programs. This is a bank scenario. That are going through the database management system that are getting at the database. And they're just retrieving the information that's centrally located. So the database management system, we also covered yesterday, so this is a little bit of review, provides the central common functionality for the data. So it's the inserting, the updating, the retrieving. So instead of saving files in this old file-based system, instead of like, file save, file open, opening, saving, closing files, we do this. We look at inserting, updating, retrieving, and viewing. So Oracle is a relational client-server database management system by default. And so when you install the Express version on your computer, you're installing both the server and the client module. And it's really the server module that's the memory-intensive module. It's designed to store a lot of data. It's designed to service like millions of clients. You're putting in together an infrastructure that's designed for massive use. It's not really going to get that on your computer, but it would on the server, so it makes sense to install it on the server system. So types of database systems, the hierarchical type. In terms of assignment number, and let me take a look here at our assignments, because some students are assignment oriented. I believe it's number 4. Let's take a look here real quick. Number 4 is the one that I wanted to highlight for you right now. In assignment number 4, it's a writing assignment. We're skipping 3 now because 3 is on SQL, which we'll be doing after lunch. But for assignment number 4, and this is why I'm showing you the assignment because I'm actually covering some of the material for it, comparing and contrasting the generations of databases. So we have the hierarchical, the network, the relational, and the object-oriented databases, which are the ones I want you to compare and contrast. I'm going to talk about hierarchical in a few minutes. I'm going to be talking about relational as well. I've talked a little bit about object-oriented, but I haven't done very much with it, and I'm not going to. Instead, I'm going to leave that to you to research, because that's a highly changing, evolving field right now. And look, what's available today wasn't available 6 months ago. So it's definitely cutting edge. What you're doing is you're going to write a research paper, and the research paper is going to be 4 to 5 pages in length, and it's going to be double spaced. So what is really, that's cut it in half, so that's 2 to 3 pages in length if it's double spaced. In terms of its volume, you can provide a graphic illustration to demonstrate the concepts, but don't fill it up full of pictures. It has to demonstrate the concepts, and the concepts that might be demonstrated might be a comparison chart. So you have hierarchical, relational, object-oriented, maybe on the vertical column, and then horizontally you might have columns that might go speed, efficiency, ease of use, or some criteria that you're going to use to compare the 3 models together or against each other. And when you do that, that makes it so that you're illustrating or you're demonstrating the concepts. And the idea is to investigate and learn about these features in the implementations and the designs, and make sure you include the following. So this is kind of the content that I want you to put in there. You want to provide a complete overview of the 3. The 3 that you're going to overview are hierarchical or networked, which is sometimes refers to the same thing. Sometimes there's a little bit of distinction between the two. A network, you can have a hierarchical non-networked database system. It doesn't necessarily have to be networked. The relational model, which is what we've been talking about, we'll continue to talk about in this course. And then the object-oriented databases. And then the first thing people go, well, which object-oriented database? It doesn't really matter what vendor, what author, what programmer put it together. It's the concept of the object-oriented database in general. So you're going to get a couple of different views and a couple of different object-oriented database examples when you go research this. So I highly recommend just following one chain or doing a comparison among all of the different object-oriented databases. But you're going to get some conflicting information in the area of the object-oriented databases because it's not a standard. And there's a couple different views of trains of thought on that one. So it's not necessarily as straightforward as you'd want it to be, which is good. It makes it interesting. So what are the various similarities, the differences between these? These do not have to be the columns in your table if you put a table together. This is just information that you want to make sure that you cover in the paper. What makes the database design unique or different? Double space your paper. Provide references for all of the information you found and used. If it's not yours, reference it. So if you provide a paraphrase or if you provide a quote from another source, make sure to provide proper credit where credit is due. Include a bibliography page at the end of the paper so I can see your sources. Unless you are all experts on object-oriented databases, which I don't think you are, you're going to have some reference sources. You may not have any on relational, you may not have any on hierarchical network, because you probably can't find anything on hierarchical. You can find a ton of stuff on relational, but you probably know that one already. So it's the object-oriented one that's going to be the most difficult to compare. So you want to provide reference citations. You want to write the paper in your own words. Now, I didn't really think about it, but the last time I gave this assignment, well, not the last time, times before, when I said write the paper, people thought literally, oh, we have to handwrite it? Type, write, create, use your own words when you do this. You don't have to physically write the paper. You can actually type it, word processor. Yeah. But I thought that was funny that people thought you had to handwrite it. No. So write the paper, create the paper. If you plagiarize, this is the one thing that's going to go through Turnitin.com for this course, I believe. So I'm telling you ahead of time, it will be put through a plagiarized checker called Turnitin.com. It does it automatically. It will mark your paper if it's plagiarized. So, and plagiarizing means not only intentional but unintentional. If you don't quote, don't use quotation marks, paraphrase too closely to the original, or use too much of original work that's not yours from your sources, the percentage will come back too high. If it comes back too high, and I don't know what the percentage is supposed to be set at. I don't know what people use. I think it's like 40 or 50%. It's very generous. It's very generous. It's not like 1%, 2%. You don't have to get like a 0. And there's a way of pre-checking your paper if you want to by going and running it through the system and seeing. There's the school library services has a Turnitin.com student sign-in procedure, student sign-in count. I'm not really familiar with the student end of it. But they do provide access to the system, so you can run your paper through and can check it out. If it's below 40%, I think, 50%, which is pretty high actually, that's like half your paper is plagiarized, then you're okay. If it's above that, then it's an automatic 0, so you get an F on it. Don't consult with others. This is an individual, not a group paper as well. So don't turn in the same paper as somebody else. That will also have a problem as well. So that is assignment number 4. So let's go back to the material that relates to it. And again, all of the assignments are due at the end of the course on August 22nd. And there won't be any new assignments or anything. These are the ones that go. So you're able to probably knock out about half the assignments after the first weekend. So, because the second weekend is going to be more hands-on, and the third weekend is going to be the final exam weekend. So now we're going to look at hierarchical. So if we look at the hierarchical, the data relationships are maintained using pointers normally. In fact, it's sort of like inodes, or sort of like a Unix file system actually. So we create pointers, or pointers that create links using physical hardware locations. And we connect the data together using a pointing kind of system in, just as it sounds, sort of a hierarchical fashion. This data points to this data, that points to this data, that points to this data. So we'd have a pointer at the beginning that would say, oh, this is the student data. And then in the student data, we'd have the first name, the last name. And imagine it's sort of like set up like a tree, actually. The structure of the hierarchy determines the locations that all of the data is going to be stored in. Very similar, and it was the foundation for the relational model. Only thing different is the relational model took and flattened it all out. There's no hierarchy in a relational model. All the tables are flattened out, and then they're keyed together. So they're keyed together with primary and foreign keys. So the linkage is through the key system instead of the hierarchy. If we create a hierarchical structure or a tree of the data, then we don't need the keys. We have the linkage. We have the pointers that go from, when we go into the student table and we look at student A, we have the linkage right there to follow it down the hierarchy to go to the next piece of data. And then what we're looking at is tree traversal. And if we look at tree traversal, then we look at, well, how efficient is that? And so efficiency, speed of searching, speed of finding is slower because of the data format, because of the data structure we created. So the hierarchical ended up being slow, and we add more data to it, and we ended up with situations where queries take too long. It's too slow. So they improved upon the concept by making the relational database system, flattened everything out. Now we don't have to go through 12 layers of branches to get to where we want to go to. But now we have to worry about, well, what happens when we join the tables together? So in the relational model, your efficiency and your problems usually come with projections that are made on joins. So when we join multiple tables together, that operation is computationally expensive because of the query time. And so then a lot of people have spent, in relational database design, a lot of time and energy on query optimization. So most of the research you'll find on relational database will be all in the area of query optimization and efficiency. How do we make those queries run faster? And then what ended up happening is, centuries later, we've outgrown relational. Now we have big data. We've got tons of data. Now the relational model is slow. So we're having the same problem, which is actually kind of interesting. We're having the same problem we had maybe about 20 years ago with hierarchical, or 20, 30 years ago with hierarchical. We're having it with a relational model. The relational model is not good anymore because it's just, you can't query and wait an hour for the results to come back. So as data just keeps getting bigger and bigger and bigger, we're switching to different mechanisms and ways of getting at that data. So now we have data mining techniques and big data kind of concepts in terms of new techniques to search through, to house, to store, and to organize the data. And it's mostly more of an object-oriented fashion. But object orientation is probably not going to be the solution either, actually. So anyway, think of the hierarchical as pointers and a level system with a tree and a branching concept versus the relational where we have maintained shared data values called keys. Now, relational model, and you're gonna hear, I've been saying so far that redundancy is bad, duplicate data and redundancy is bad, but relational model is built on that because we have shared keys. So the way that it's normally described in most database books is that it's called controlled redundancy. So it's controlled redundancy because we put the redundancy in on purpose and we're controlling it. Because why do we need a student number in every student number in every single table we have, so we can link the students together? So that's like controlled redundancy. So it's duplicate fields that are used over and over again. So here's your example of a hierarchical database where we have parent data with pointer to child data. And you see it's different levels. We're storing pointers at the different levels. The pointers we follow, it's sort of like a linked list actually. Think of a database implemented sort of like a linked list, where the main customer data is going from a pointer to the account data to the loan data. Maybe they're both pointing to the same one. This table here could be the parent for another child. Here we just have one parent and two child tables that we have down here, but it's just a pointer essentially being used. So sort of very similar to a linked list implementation. So in the relational model, the data is organized into tables as we've seen before. We built them yesterday with entity relationship diagrams. And the organization, and the reason why we looked at entity relationship diagrams is because that gives us our table relationships. An entity is a table. An entity is also an object, actually. And it gives us our way of thinking for organizing the tables. So if we're not going to look at a hierarchical structure, and that's an organizational structure, you can't create an ERD diagram to create a hierarchical. Instead, it follows more of a networking file structure system, which is basically, if you think about the file structure in Linux, Unix, most of it's pointer based actually these days, and it's hierarchical. Very similar to a database actually in the old-fashioned days. Now, if you're thinking about, well, how do we design a relational database? How do we get a relation out of that? Well, then the thinking definitely comes 100% from entity relationship diagramming. So it's the thought that goes into the relationships between the data. How are you going to link the data together? And the linking of the data is through those keys. And how are we going to get the keys? Well, it's from this entity to that entity. And how many tables do we need? Well, it depends on what the relationship is. What degree of relationship? Is it a lot? Or is it just one? If it's one, we don't need an extra table to hold that. We can just stuff it into the other table, that already exists. So we're looking at those columns and those rows, and the columns represent the different data categories. The rows represent the actual data values themselves. Here's a little example. Cheesecake example, plain and cherry cheesecake, quantity on hand for a restaurant, let's say. The product number and description. Sometimes referred to as fields as well. So our relational table keys, our primary key, most people are familiar with this one. I talked about yesterday as well. Uniquely identifies a record, must be unique for each record. Cannot be null. Null is the word we're using for undefined. So a lot of the queries that we'll be making after lunch will be, specified not null. So the concept of the constraint is going to be implemented with the queries. So a database constraint comes in a couple of different forms. The one that we can put on a table is the one that's going to say this field can't be empty, or this field is the primary key. If we specify the field as being a primary key in a table, when we wrote the SQL statement to create the table, we said this is a primary key. Then we get an automatic index. And then we get features that are associated with it as a primary key. And if we do that, then we can take and associate it with what's called a foreign key automatically. So what ends up happening is most people figure out, oh, I can write the SQL statements, no problem. Oh, I don't have to say it's a primary key. I can just use it like a primary key. But then you don't get your index because you're not following the format that you're supposed to be doing to optimize the query. And to optimize a query, you want to actually designate a primary key and designate a foreign key. If you do that, then you get the database working for you instead of you working for the database. And you get the database optimized and indexed according to, in the memory, everything is formatted correctly and it is designed for your use. And so that's when you say something is not null, you have the database constraint of it not allowing any entry to be put in. So the more protective you make the database table, the more constraints you put on it, the more reliable it is in the long run. I talked about the concept of the candidate key yesterday as well, and I said probably not a good idea to have so many candidate keys in there. You don't want any. Fields that could be used as a primary key. So they call them candidate keys, because when you look at the table, you go, and you're not the database designer, you didn't put the table together, someone hands you this, I say, hey, look, here's the table, here's the fields, and I see social security number and I see primary key, I see student ID. They're both candidates by definition, because either one of them could be the primary key, but I don't know which one they are. So then, that's what that means. That's what a candidate key means. A surrogate key is one that acts like a key when no key exists. So it's a usually numeric field created for purposes of being a primary key. It's not an index, and it's not a sequence. So I'll be talking about those later today as well. It's nothing more than a surrogate. It's a key for when a key doesn't exist. The first 4 characters of your last name, along with the last 4 characters of your social security number or something. So usually it's a number sequence of some sort. So the foreign key, so a field in a table that is a primary key in another table. So you actually designate it as a foreign key. When you do that, both tables gets indexed on the same table. A foreign primary relationship creates a faster join. So the join actually executes faster because you have the parent-child relationship with the foreign and then the primary established. So it creates a relationship between the two tables. And the foreign key values must be exactly matched with the primary. Otherwise, you can't put an entry into the table as well. So here's an example of the table relationship with a primary foreign key, where we have product ID and product ID matches in both tables. So primary key in one table and a foreign key in the other matches identically. So we have product IDs here that match up. So it's nothing, and that's why I say it's called controlled redundancy, because this is redundant. And most people go, I thought you said you don't want duplicate data and you don't want redundancy. Well, it's redundancy that's controlled because there's no such thing as inconsistencies here. If this was actually a primary key and this was designated as a foreign key, then there's no way that it's going to be not matching. So we're not introducing any problems. talked about yesterday the concept of the composite key. That's when we linked weak tables with strong tables normally. You don't want to put a composite key in there if you don't have to, because you do it for a reason for linking, actually. And here we have one. This is a primary key made up of a combination of 2 or more fields. So a composite key of example, order ID and product ID. The key isn't actually stored in the table. It's a composite. So if the order ID changes or gets added new one in, it automatically gets updated with any new product ID that might be added in. So it's not pre-established ahead of time. It's established on the fly as a composite of 2 existing columns in the database. So that's the extra key information I wanted to give you. So let's talk about database system architectures, because this is Oracle architecture and administration. So this is a little bit of architectural stuff. We have mainframe databases, personal databases, and client-server databases. As I mentioned before, Oracle is a client-server database. Both of them run a mainframe system. Both the database management system and applications run on the same computer. Users access the databases, and they're using terminal windows normally to do that. On the personal database, we have everything running on both workstations. So the application runs on the user's workstation itself. In the client model, what we have is the centralized server, and the applications run on the user's client workstation. To supplement the information that's not written on this slide, but is more relevant towards networking, right now we're thinking of it as more of an n-tiered server environment, where we have a web server, then we have an application server, and then we have a database server. So dedicated servers tiered with multiple purpose functionality per server gives us better fault tolerance, gives us better scaling. So the data applications can grow, the database can grow, the web services can grow, and it's all separated out and tiered so that one server connects to another server connects to another server, which is the common way of doing it these days. And then you can protect the access between the servers. So a user can't go to the database server. Has to go through the actually has to go through the web server if it's coming through a web interface. The web server goes to the application server. The application server goes to the database. Puts it further back, and it puts it further back. It makes it more secure. One of the biggest things we have to deal with the internet is security. So if you tier it, you can put special access between everything, gateways. You can put, routers that are intelligent, that do virus scanning and, port sniffing and stuff like that, so we can make sure we only get, reliable connections coming through it. Advantages of the client-server database: handling servers and client failures. We can separate everything out by client and provide single access with different levels of security, different levels of privileges. Process transactions, processing the transaction itself, handling high volumes, protecting and providing the security as I just mentioned, and then servicing multiple simultaneous users. Also not mentioned on this is that we could also set up multiple database servers. So we can have a production database server that's mirrored or duplicated on a staging or a testing server, and then swap them back and forth for fault tolerance or for testing purposes or for anything we really want to do with it. So if we modularize it out, we can use multiple servers. We can actually have multiple databases with multiple vendors, actually. We can have a MySQL server with an Oracle server, something else. So actually, I should put MySQL out on the server that I'm going to build. It actually runs better, and it's free than Oracle, because it's very similar, actually. I should put a MySQL out on because it works with Apache. I should put that on the CS server. I'll put them both, hopefully. The problem, though, is when you install multiple databases on the same server, they all try to go on the same ports, and they conflict with each other sometimes. If you're running it through a server like Apache server interface through it, you're going to end up with problems. I'm going to end up with problems with it. So maybe I'll do a MySQL on that, because then that would work out quite well for for HTML, CSS, and for programming courses for the web, actually. So most people, if you're not familiar with MySQL, it's sort of the open source version of Oracle. I shouldn't call it that though. Oracle's a commercial-based product, has a lot more features, has a lot more functionality. MySQL is the open source solution for those who used a lot in web development actually, who want a cheap database that has most of the functionality of the Oracle system actually, but it's affordable for companies. Not very secure, lacks some of the security features, and lacks some of the sophisticated applications that work with it. But PHP admin is actually kind of interesting for it. So I'll put PHP admin on my server, my dream server when I create it. So I got a lot of work ahead of me. The Oracle environment on the server side, Enterprise Edition on the central database server, or Oracle Personal Edition. I can actually install the Oracle Personal Edition. The only problem is only one person at a time can log into it. It's not meant for widespread. And to buy licenses to support that is looking at about, I don't know what the prices are today, but it used to be fairly steep, like $3,000 or $4,000 for like 10 users or something. It was fairly steep. So, but if you're a bank, you're going to install that. You're not going to use an open source database for a banking application. You're not going to use open source for anything that you want security for, essentially. Otherwise, you're just giving the source code away, and you're giving you're pretty much telling the world that you didn't spend too much time and energy on that application either. Let's see, Oracle Personal Edition is the one you're probably going to be more familiar with. So the environment on the client side, so the server side is just this database that's installed, that's out there running. On the client side, we have SQL Plus, and which we're going to look at today, and PLSQL, which we may not get to till the next class next weekend, but we also have this product called Developer. Oracle Developer and Oracle Tools do not come with the personal version of Oracle. So this is what you pay the big bucks for to go to the Oracle training. And what you get is a procedure builder, form builder, report builder, graphic builder, project builder. So I'm not going to really focus on the tools because they're about $3,000 or $4,000 to purchase Oracle Developer. No one's going to do it. So. And if you look at the case study databases, when you install Oracle, you actually get sample accounts. There's an HR account. There's a Clearwater's Traders, Northwind University System. They put together actually some sample case study databases that show you examples. So it kind of gets you started a little bit. If you look at them, you see basic tables for customers, customer orders. So one of them, the Clearwater, is on a customer retail kind of inventory shipments sort of example. The university is one that's going to have faculty and students, and they're classic teaching examples actually. The retail sales, the retail store, the university setting, and then the software experts database table is just going to be like a project management kind of table. Skills, clients, projects, evaluations, and stuff as well. So that's my spiel on an introduction to the client-server relational versus hierarchical database model. So that was number 2A. So we'll switch now to 2B. And 2B is on creating database objects. So in Oracle, you actually create an object, and inside of the object, you have views, and you have tables, and you have users, and you have a bunch of other things inside of it. So although we're looking at a relational database model for the data storage and manipulation, we are looking at an object-oriented sort of model for the working with the concepts. So it's all about the database objects. So we create a database object, and we give it a name. So the database object might be called something like HR for human resources, and or sales, or marketing, or research. And then Oracle Database module itself, or object, consists of multiple user accounts that are associated with the object. So you grant access on the object to the user. You put a user inside of the object. So each user account owns a database object. If you have a user account that's, for example, the admin. So in the old Unix Windows, Linux, kind of, well, most operating systems now have admins, and you have users, and you have different levels of privileges. Well, you have the same thing with Oracle as well. So think of this more like a server, actually, a server environment. So you can have a higher level user, an admin user, who owns the HR object. And then inside of the HR object, you can create user accounts that all follow a certain profile that you put together. And the profile is going to have privileges. And the privileges are going to be associated with what components in the objects can you have access to. And in Oracle, it's really an all or nothing. So users can have access to tables. Well, if they have access to tables and they have access to columns inside of tables, they have access for everybody. So that's why the view comes into place. So tables, and I'll talk about views a little bit more when we look at the queries and stuff. Views, stored procedures, which are little programs that can run inside of the object that do stuff with the database tables, essentially. And all of these things that are housed inside of the database object. And then we have the queries. So the database query is the command that's performed an operation on the database object. So after lunch, when we probably might start it before lunch, but today's all about SQL. And so when we write these queries, it's not like writing a program. It's not like programming a language. Instead, it's opening up a command prompt, a command shell window, and you're typing a statement. And you follow the statement by a semicolon, and then you type another statement, and then you type another statement. So what we're going to do today is actually look at how to write these statements. And this is how we're going to communicate with the database. So we can create, modify, view, and delete things inside of that object. So the first thing we would do when we installed Oracle is create the objects. So HR object, and the objects representing departments or features that we're going to offer in the database. And then inside, when we create the tables, and then we create the views, and we populate the information by the applications. So SQL is the language, standard query language for relational databases. And as I mentioned before, they come in two forms. Today we're going to be focusing on both, but we'll start out with the DML, the database manipulation language. And that's used to insert, update, delete, view database objects. And then to create and modify the structure of the database objects themselves, we use the DDL. DDL would be something, create a table, drop a table, truncate a table. Here we have used to create and modify the structure. So create, alter, drop. And they're executed as soon as they're issued. And you do not need to explicitly save them. In the DML category, we normally save them in text files because it's kind of like command prompts that you're typing in. And do you want to remember every time you do it what you did? Probably not going to remember it. So a lot of times people document it in text files, and then they open up the text file and they run sort of like a script, actually. You run the commands from the text file. You either cut and paste and put them in there, or you just open up the text file from the command prompt window and run the commands from there. So we'll look at how to do that as well. But they're not really saved. So they're used to insert, view, update data. And the concept of the rollback and the commit works with them. So DDL commands don't have any information saved about them. The DML commands have rollback and commit features. So when you type in a DML command, which is why they're separated out, well, not why, but one of the unique features associated with the separation is that for a DDL, commands need to be explicitly saved or be rolled back. The DML could be controlled through some transaction processing, which says, if this one passed, if this one passed, if this one passed, then commit. Otherwise, roll back. And that's what we use languages like PL/SQL for, to kind of organize the flow of the commands and what's going on with that. So we'll look at the concept of committing and rollbacking as we go through the process. Commit means save the changes, rollback means undo the changes, for the most part. So we also have user accounts, and so each Oracle object user has a user schema associated with them. So it's the area of the database that the user's database objects are stored. It's their space in the database object. and identified by a unique username and a protected password, obviously. So each user schema is granted specific privileges on objects and different objects. A user of one object might be granted privileges on another object's tables or views or things. So we have different types of database privileges that are set up in Oracle, and this one I'm giving you is very Oracle specific now. System privileges. So we can control the operation that the user can perform within the database system. Connecting to databases, creating new tables, shutting it down, doing that sort of process. That's what we'd call system privileges or system administration versus object or user privileges. So granting on individual database objects. So we have object control as well. Controlling operations that the user can perform, when to create an object in the user's schema, granting privileges on objects, things of that nature for users. So just think we have system and we also have object privileges that are associated. There's a naming convention to the names of the users and the names of the objects. Just like any programming language, we have a naming convention. 1 to 30 characters long, must begin with a character, can't begin it with a number, and can contain character, numbers, and symbols. So we can have some symbols that are also put in there. It's a little bit less strict than a programming language like C, but very similar, follows a very C-like naming convention. So let's see what we're going to do here. So creating a new user account. So the first thing we do is create the objects. The object is generally created by the system privilege, by the user with the highest system privileges or the admin. So admin comes in and says creates HR, and then we create sales. And actually the command is very similar to that. It's create HR, create sales. Or you're using a GUI interface for it. But for the most part, even today, the command window, the SQL Plus window, is probably the most highly used feature. Although you'd think GUI would take over everything these days, not quite as efficient, especially if you're telecommuting or you're logging into a computer that's in New York, a server, because the server is not going to be at the same location perhaps so as the company, or it might be, who knows. You might be sitting at a terminal prompt in front of the database server typing stuff in. But this is the window you get. It looks like that actually. Well, the current one has different Windows motif, but yeah. This is called Oracle SQL Plus. It looks like a DOS prompt or a terminal window. You open up the window and you get a little cursor that says SQL. If you're going to tell that into a server, you're going to get a little prompt and you're going to type in Oracle. You're going to type in MySQL, and then you get another prompt that says MySQL with a little arrow, or Oracle with a little arrow, or SQL with a little arrow. It tells you that you're inside of the server for the database. So you log into the server, then you get a server prompt. So from one server you log into the other server. If you think about a nesting kind of concept. And then you've opened up a shell inside of the other server, and then you're typing in. So this is very much a shell exposure. And the shell takes on, if this is the Oracle SQL Plus window, it takes on standard SQL statements plus PL statements plus any Oracle related statements. So we'll go through the plus a little bit more in detail after we go through the basic SQL statements. But there's a handful of plus. And the handful of plus is actually from, the one I use the most often is describe, DESC, describes a table format. So you don't have to imagine what the format looks like. You can actually see it. So here's the syntax to create a user. So create username identified by password. And so in the SQL window, you type in create user L Howard identified by ASDF as the password. And then it comes back and says, okay, user created. That's the instant gratification you get. So, okay, user created. All right. That's basically the job of the DBA. Create users, create the database objects. They're the ones who are actually manipulating what's in the database. They're not necessarily designing it, but they're controlling the access to it. So example of Oracle system privileges. And these are things that you would, after you created the user, then you would grant these privileges. You use a grant command to actually do that. So the privilege here, and this is the level and this is the purpose. there's a little scroll here, so the L actually word wrapped down one extra line. So examples of Oracle system privileges, and these may have changed throughout the years, but this is a basic set that still exists. You can create a session or connecting to the database. So some users won't be able to connect to the database, which is kind of, well, from a user perspective, you're like, well, why would you want to do that? Well, if you're running a report module and something else is connecting to it, you could still be logged in to the system but not connecting, not given privilege to anything at all, which is kind of not so functional, but it does come in handy when you want to provide a more protective mode. Creating tables, so you're going to let them connect, but you're not going to allow them to create tables. So I believe it is attendance time, so I'm going to pause this video. Okay, I'm back, and we're going to start back up where we left off, I hope. Alright, so I was talking about examples of Oracle system privileges, and the privileges can be set in any number of ways. And so we can create a session, create a table. These are all the privileges themselves, all applied towards users, and all the privileges. This is just a sampling. So we can give users the privilege to create tables, drop tables, have unlimited table spaces, which means they can add more space to each one of the sections or objects that are holding the database schemas and stuff. Create users, so a user can create another user. That is a dangerous privilege to give. Grant any privileges. So I guess they could grant themselves a privilege. Create any table or drop any table. So basically, the system privileges are to hopefully provide a level of security and then also a level of functionality that goes along with it per user. To grant a system privilege to a user, you would use this privilege statement here where it says keyword grant. This is the SQL Plus, by the way. It's SQL statement, but it's in the plus category. So creating a user, grant create session, comma, create table to L. Howard, grant successful is a way of saying, well, for each one of the built-in system privileges here, we're going to grant them to a user. And this is just an example of doing it, granting privilege 1, privilege 2, privilege 3. Or you can grant all, and grant all privileges. The privilege that you're granting would be associated with one of these predefined privileges that's going to be in the system tables. So, actually, the default user for Oracle is system. The name is system, and they're called system tables. And the table, everything is actually stored in the form of a table in Oracle. So this is a table that would appear, and in the table you could put an entry to add your own. So you can actually add your own privilege. If you added your own privilege, then you would be able to grant your own privilege as well. If you added one to it, and it would be a predefined privilege that would set certain access levels and certain features per the privilege. We also have roles that can be defined. So a role in a database object that can be assigned system privileges. So instead of granting each one of the system privileges separately, we can combine them all together and call it a role. What's the role? It might be a TA, teacher, student, where they would be using the system in a sort of the same context. So all students would have the same role, all the TAs would have the same role, and then the role would have grant privileges for certain things that they can do. Look at grades, but they can't change grades, upload assignments, change assignments, stuff like that. So the role is the database object is assigned to system privileges, and then the role is then assigned to a user, and then the user inherits all the role privileges that are associated with the role, and choose to easily assign groups of related privileges to users. So here's an example of creating a role. So you would say create role, role name. So you create a role. Here we have Oracle student. This is role created. So we would type this stuff in, and this is the feedback we get, and then we go back to a prompt. And then assign privileges to a role. So you create a role, and then you create table to Oracle student, which would be creating a privilege for the role. And then you assign the role to the user. So it's a hierarchical kind of way of setting the privileges. So you'd grant privilege 1, privilege 2, etc. that you could also create as well, create privilege something, to the role name. So here we have granted create table to Oracle student, and then we would assign the role to the user. So grant role name to username. So then we have grant Oracle student to Al Howard, which is the user that we created in the first step, actually a few slides ago. So if we can assign them all to a role, it's kind of like a profile. So roles and profiles are sort of the same thing, and the roles we would have, for example, HR role, perhaps student role, TA role, system administrator role, and they would all have these different privileges attached to it, and then you take the privilege, or the role I should say, and attach it to a user. And then you can create groups of users that all have the same privileges that are associated with it. So just like you can grant, you can revoke, take away. So revoke privilege 1, 2, 3 from user. And actually you can grant a role to a user and a privilege to a user separately. This is where people get into trouble when they don't follow rules. So the DBA generally is the one setting the policies, establishing the roles, and then you're not normally granting privileges along with a role, because you can grant a role to a TA and then, let's say for example, grant a bunch of privileges that are not associated with the role to the TA. And then you got a TA that's got too many privileges that are associated, and then they look at that and they go, oh, it's a role. He or she's got the role of the TA. But then they also have these other privileges that are granted to it, which kind of violates the rules or the policies associated with what kind of access you want to give a particular user. So here's revoking privilege 1, privilege 2, etc. from a user. So you can grant and then you can revoke. And so these work in SQL. They may not necessarily work in other databases, but they're Oracle-specific SQL statements to revoke create table from Al Howard. You can also revoke a role. So revoke and grant are the opposites of each other. They work with roles and privileges. And you can grant or revoke either one. So administering system privileges. To be able to grant system privileges to other users, a user account must have been accessed, or it must be granted the privilege with the admin option. So we make certain privileges admin accessible. We grant admin to certain users. So you can have more than one admin, essentially. And then that person can grant and revoke privileges for other users. So grant create table to L. Howard with admin option. So we use with admin option to say that this L. Howard can grant create table. He can also grant, or she can actually grant that particular privilege to other users as well. So once you have the privilege, you can grant it to other privileges, which is how you're going to control the configuration of all of the admins that are working per department. So you don't have the database guy doing everything. So you can kind of give the teacher the ability to grant, let's say, something to the students, or the TA the ability to grant to other students or something. In terms of defining the database tables themselves, you create the table. You must also specify the table name, the field names that are going to be inside of the tables, the data types, the field sizes, and any constraints that you're going to put on there. The constraints are going to be the primary key, the foreign key, and unique. And I'll talk about unique today as well. Unique is not a key. Unique is just basically saying it's going to be just like a primary key. Unique and primary key have a lot in common, actually. Unique just says no other row can have the same value. It has to be a unique value. But it's not indexed, so it's not used like a primary key. So it's just basically like it's a hybrid key that can be used, but don't search on unique keys because you're not indexed on it. And if you're not indexed on it, it's going to run slower. So, which is what a lot of people do. They make it unique, and then they run a query on it, and they go, if you just made it primary, the whole query will run so much faster because you're indexed on it versus that unique key that you put in there. So, must follow the Oracle naming convention when you create tables and field names, and each table in the user scheme must have a unique name within the user schema. You can have the same table duplicated in other objects with the same name. So you have staging object. Staging object has table A, table B, table C. Then you have deployed object, has table A, table B, table C. It can be identical as long as it's unique within the objects, which is actually kind of like users. Users can also have their own unique tables as long as it's unique within the user, which is interesting as well. So we have a lot of confusion that comes into place when we have duplicate objects and then they have duplicate names, and then what object is this? And then you have to know what object, because you can easily switch objects and all the applications are going to work the same because all the table names are the same. So you have test object and then you have deployed object, and you just swap the object, and everything inside the object is identical, but one's for testing purposes and the other one's for launching. So it's the same thing. So each table in the user scheme has to have a unique name as well within the user scheme, and each field in the table must also have a unique name within that table, but you can use the same names across multiple tables. Lo and behold, we have these Oracle data types. Actually, they've gotten better over the years. They've been reduced down into fewer numbers. So the data type is a specific type of data that's going to be stored in the field. We have about 5 different or 6 different date formats. And we have character formats, number formats. We actually have about 3 or 4 different character formats as well. And the uses of these data types is for row level constraints. So we make sure we can do error checking. We put a name in and not a number, or text in instead of a number, or we put something in there that was a telephone number instead of a zip code or something. Efficient use of the storage space as well. Same thing, reason why we give data types in programming languages to variables, and we use it per type. We do the same thing in Oracle to essentially use the correct data type. Variable characters, probably the most popular one that you're going to use, but you're not going to make every field text or character type. Variable character, there's also variable character 2, which is the more current version. It hasn't really changed. You can still use var character. It just means multiple characters. Variable character strings, maximum of 4,000 characters. Must specify the maximum width allowed, which means it's going to be 15, 20, and how many characters are you going to have in that space? And when we see SQL examples, we'll see that being used with the create table command. No trailing blank spaces are added to the end. It's just truncated. All you get are those number of characters that you put in, which is different than some other databases where you get trailing spaces up to 15. And then you constantly have to left trim or right trim something to get rid of those extra spaces. Here's an example of a student name that is a variable character 2, length 30. So you use opening and closing brackets here to specify the length. So we put it here 30, which means the name can't be more than 30 characters long. We used to have a W character, wide character, which is basically just specifying the character length or character. W character is probably the more common used. Each one of your databases is going to have different data types. So MySQL will have slightly different data type names than Oracle versus another database that's out there. In terms of the character, it's also a fixed length character data, not string, or not meant to be string, and it's a smaller, so it's 2,000. W characters like 3,000 or 4,000 or something like that, characters in length. And must specify the maximum width as well, and also adding trailing spaces adds a trailing space, blank space, to pad the width. Variable characters does not add any any trailing spaces. So if we said 30 but the name was only 10, there's only 10 characters in there. There's not 30. The character, though, is if it's expecting 2 and you only give it 1, you get 1 with a space next to it. So you always get 2, which is a smaller space, which is more time effective, which is why there's 2 different variables. I should say space effective, space efficient. So this one only reserves the amount of space needed. This one always reserves the identical amount of space. So if it's 1, there's a blank space for 1. If it's empty, it still has a space in it. So it adds that 1. Why do you want that? Because you're going to read it. And you're only looking for 1 or 2 or 3 or 4. You're not looking for 30. You could make this 30. It holds up to 2,000 characters, but you're going to store a bunch of blank spaces at the end of it. So most people would use the variable character. You can even use the variable character for 2, and then it's going to be empty completely. Which, if you run a query and it comes back empty completely, you might end up with an error message from that query. Especially if you're using that query result in a web form of some sort, you might end up with a problem with it. Long story short, you want to choose your character data types wisely, same as your date types, because the way you define the field is the way you have to enter the data into the field. So if you can't get the information in easily, then you might end up with a problem from an application perspective and not really a database problem. Your application designer is going, how do I get the dates in here? How do I get the characters in here? It keeps coming back on an error message. It's because it's a variable character. You have to give it something, otherwise it's going to come back with nothing. Or it's a character. So here's our character. So our N character supports 16-digit binary character codes used for alternate alphabets. So this one is if you've got different alphabet sets for foreign language support, you're going to use an N character. Lo and behold, we have the number data types. We just have number. Number stores values between 10 and 130 and, well, 10,126. Well, that's enough numbers. If we want precision, we can specify the precision. So we can say number, precision, comma, scale to declare the format as well. So number data types. Number data types come in the form of integers, floating points, fixed points, if you specify the precision and the scale. The precision is the total number of digits on either side of the decimal point, like 7, 3, kind of like naming conventions. And the scale is the number of digits to the right of the decimal point. So it's usually 2 digits to the right for money. So you can go 7, 2 or 10, 2. Depends on what level of precision you want to the left or to the right of the decimal point. Why they call it precision and scale, I don't know, but it makes more sense, I guess. If you don't, if you just omit the second, then you've got the scale that's omitted, and you're just giving the precision. I want 2 digits. So the whole number with no digits is to the right of the decimal points, and the precision is the maximum width. So we have here the scale is omitted, so we say that the age is going to be 2 digits, 12, 13, 14. It doesn't truncate, it truncates, it doesn't round. So if it was 12.5, then it's 12, or 16.5, then it's 16, or something. 16.9, 16. Just gets rid of the 2 scales. So the fixed point contains a certain number of decimal places. So the precision is the maximum width, and the scale is the number of decimal places. So we have the item price, which is a number, 5, 2, which means we're going to have the 50 cents or 45 cents or something. 2 precision past it. And we have the floating point, which contains the variable number of decimal places as well. It's just going to be done the same way. The precision and the scale are omitted. So if you omit it completely, you get the full floating point. So we have S student underscore GPA is going to be a number. We omitted the precision, so we get the entire floating point number. So it's better for rounding, or better for calculations, to keep all the precision of the entire number. Lo and behold, we have the date format. This is probably the most confusing part, because when people start inserting the data into the database, they figure, what format was that date in? You have to give it the right format of the date in order for the date to come in correctly. You also have to give it the right number format. So if you have a comma 2, you have to give it a .00 when you enter the number in. Most database systems these days will take and create the number for you, automatically add the .00 for you when you put it in. But sometimes the entry of the data into the database becomes tricky depending upon how you formatted the field that you're entering the data for. Here, a date is a date. It's not a string character. So it stores the dates in, for example, 4712 BC to 1231. Well, there's the date range for you. It stores both the date and the time component together, which is nice. So the default format is day, month, year, hours, minutes, seconds, AM, PM. As an example, 05 June 03, 12 o'clock midnight, or AM. So a sample declaration would be a student underscore date of birth with the date. And the format here is followed by date, which is going to give us our defaults. We can specify the date and time values ourselves. So if no time value is given, then the new date is inserted. The default value is 12 o'clock AM. Why do you want that? Well, there's a lot of databases out there that just leave it at the default, and you just see the date with a time, and the time doesn't mean anything. So it's extra data that's actually being stored for each one of the dates that you put in there. If no date value is given, then the new time is inserted. The default date is the first day of the current month. So you put the time in, but you don't put the date in. And you have interesting formats. You can actually change the formats, and we're going to see that when we look at the SQL lecture, all the different date formats. So you can take out the time completely. You can just store the time without the date, or you can store this in a different order, depending upon how you want to put your dates in there. And regardless of how you put it in there, how you specify it, how you put it in there is going to be dependent on how you specified it. So you can make it easier or harder for your users. Oracle supports what's called a large object or large object binary for the data type itself, or binary large object, blob. Stores up to 4 gigabytes of binary data. We have actually a bigger one now that stores up to 8 gigabytes or 9 gigabytes, which is a little more updated than this slide. That is for multimedia DVD files, stuff like that. You can take an entire DVD, put it in a database, put it inside of a column of a database these days. Works great for pictures, works great for large binary objects. The only problem with this, and people are doing it a lot actually for internet applications, they put pictures and music files and videos and all this stuff in the database. Well, it takes a long time to get it out. It ruins your efficiency. So if you put it in a database, you have to think about, well, if I query the database and I'm pulling the information out of the database, that might take an hour or 2 hours to get I can put it in the database, no problem, but it's going to take a couple hours for me to get it out of the database. Maybe I'll just keep it in the form of a file, and then I put the link in the database to the file. Much easier. It takes you a couple seconds to get the text of the URL out of that. Then it can take you 5 minutes or so, and the user is willing to look at it because they're looking at a plugin and the thing's loading, or they're using HTML5 and they automatically see it. You know, a little bit easier response, a little faster response than pulling the whole file, 8 gigabytes or 6 gigabytes, out of a database table. And then not only that, but this is really going to wear down your database table and your indexing that's going to go on. So you can also do a character large binary object to store Word files, text files and stuff. A B file stores a reference to a binary file contained in an operating system, you know, like maybe ls or dir or whatever. So you can have a file itself that is stored in the database table. Or an nglob, a character of large object binary that supports 16-bit character code. So just think we can store really large objects these days inside of our database tables. When we declare a lob or clob, we have the data field itself, the item is specified. The item size is not specified because it can store up to a certain amount. So we have an item image, that's a blob, or item image, that's a B file, binary file. And we're storing the file link inside of the table, or we're storing the object itself. If we're going to store an URL, we're just going to make this text. We're going to go back to the variable character 2, and we'll just put the text in there. And we'll make it 30 or so, 35. And then we end up with a link to the file instead. So creating a database table, here's our syntax. We create table with a table name. And then we have some fields with the data types. So here's an example here. So we can create table my students. And we have, this is the name of one of the fields called student ID. It's going to be a number 6. And we have a comma. It's just as written this way for illustrative purposes. It could actually all be on one line if you wanted to. And then we have the name, the date of birth, the class. Don't worry about the syntax here. We're going to go through SQL after lunch. We're going to learn everything there is to know. We might even start it before lunch. Everything there is to know about the syntax for creating a table. But what we're doing here is including these data types, which is why this is coming up right now. The data types are all different for the different fields. We specify the data type when we create the table. So. Constraints. I mentioned it before. This is what we can put on the field. We have field constraints or column constraints. that says this must be a date, this must be text, or this must be a number. So these are rules or restrictions on the values that can be inserted into the field. So we can't get bad data in there. If one of the values isn't correct, the entire row is rejected. So it says, all right, error, error, can't put this in here. And you're like, well, why? So you can get rid of the errors easily by taking all the data types away. And then you have no constraints on it, and it just sticks everything in there. And then you get garbage populated out into your database. Not such a good result. Better to fix the input of what's being put in there. So we have the types of constraints. We have integrity, and we also have value. So the integrity defines the primary and foreign keys. If a student is in the database already, and their primary key is set correctly, then we have an integrity constraint. Because we try to put the student in again, and it's going to, oh, sorry, rejected. Student's already in here. So the integrity of the data itself is constrained by duplicate entries of students that should not be allowed. And the opposite is the value. So the specified value or the range of values. You said the character. You said that this field is going to be, let's say it's identifying, I don't know, age. And you put in there 105. And so, well, how can you be 105 and still be a student at this school? You know, maybe the range is from 0 or 18 to perhaps 99, you know, like 2 digits. This is the same thing that we had with value constraints that were put on dates, meaning that the date had to be 2 digits. And so this is the same thing we had in the year 2000 problems, you know, about 13 years ago, Y2K issues, when the databases themselves had value constraints on them. And you put 0, 0, it comes in as 0. And then, you know, how can the date be 0? So the databases were going to reject it. Sorry, you can't put you in here. You can't be 0. You have to be like 2 digits or something. And then you have to change the logic to accommodate for that. So constraints levels. So those are examples of 2 constraints that are put on rows in a table. In order to enter the row into the table, it must meet integrity and value constraints. So in the form of table constraints, we also have column constraints. So column constraints. So a table constraint restricts the values of the fields with respect to the other table records that are in there. So from a table constraint category, we have if the student's already in there, the integrity of that, you know, duplicate record coming in, it's not going to allow it in relationship with the other rows that are in that table. An example of primary key value must be unique for each record. In the column constraints or attribute constraint category, that's where it's going to restrict a particular value. If you have gender in there, you're going to want a value. The value is going to be M or F. If you put Z in there, it's going to violate the column constraint to say this is not one of our expected values. Or for example, you have the states and you have all the 2-digit character abbreviations for all the states in the United States, and you put ZZ in there, it's going to go, sorry, what state is this? Instead, you can list all of the states, and then it has to be CA, CO, or A, whatever, I don't know. All I know is Colorado and California, I guess. So, I don't know all the state abbreviations. Nobody does, actually. There's a drop-down window. You pick it automatically on most web forms. So, you can create what's called a constraint in the system and apply the constraint on the column. So constraints might have names, internal names used by the DBMS to identify the constraints. This is something you can do in Oracle. You can't do it in other databases. So this is why Oracle is popular for some reasons, for one of the reasons I could say. Each constraint name in a user schema must be unique, and if you do not name a constraint, the system will automatically generate an unintuitive name for you that won't make any sense. So here's a constraint name. Constraint name convention. Table name, table field constraint ID. So constraint ID values are for primary key, PK, for foreign key, FK, for check condition. Check a condition before you put it in, CC. Not null, NN, or unique, UK. Here's an example of a constraint name, my student underscore S underscore ID underscore PK. What is a primary key constraint as defined by its name? You would apply that constraint on the column that you are creating in the table that you're putting together. So let's look at this primary key constraint. It's at a table level because the table level is going to be controlling all of the rows that are inserted into the table. When you define a primary key, you can go constraint space the constraint name primary key, which means you're taking, you can actually do this 3 different ways. You can create the primary key when you're defining the table and creating the table using SQL. You can do it through some GUI controls, or you can do it by creating a constraint and then sticking the constraint on the column. Most people, and I actually have a tendency just to define the primary key when I define the table, and we're going to see that later with the SQL lecture. But here's an example of creating the constraint, applying the constraint onto the column. So constraint is called student underscore S underscore ID underscore PK, and it's primary key, and it's going to be on the student ID number 6. It can be 6 characters, like 6 digits long, before the decimal, no decimal point precision, and the constraint is going to be a primary key, and we're going to call it student S ID PK, because then we can use that constraint name again on another table if we wanted to. So we don't necessarily, are not required to define the constraint, but if we do that, we can reuse it over and over again. Here's an example. So we say primary key constraint here can be defined when the field is declared. So create table, my students, put the constraint on there, my students, call it this, and call it a primary key. We could leave out this part and just put primary key next to it. That's what I'm saying. We're going to see this later when we do the database, the SQL lecture, where we can simplify this process. If we name it, then we can identify this as the constraint and use this instead of primary key over and over again. So we're just here just defining this my student underscore S underscore ID as a constraint. So it's kind of a roundabout way of doing it. We don't have to do this. We could just put the word primary key next to it. Is that what you're going to ask? Yeah. It's a syntax shortcut. We'll see that when we do the syntax, when we do the SQL. Nobody, well, I shouldn't say nobody. Often, unless you're making a huge database system, are you going to identify your constraints by name? If you do by name, then it's easier to remember. We don't necessarily need to know exactly what the field is called. We can just call it the primary key, and then we can identify this is my students underscore SID as a constraint. So it's just a higher level of control. So you can also be defined after. So this is while the table is being created. We don't want to do it with the create table. You can do it after you create the table. So at the end, instead of doing it on the field here, at the end you're adding the constraint of the primary key and you're putting it on this field. Why do you have that choice? Well, because maybe you don't want to embed it inside of the create table. Because here's what happens about 20 years from now. You're going to look at this text file that you put together that has all these great tables in it. Because you're going to put this in a text file. You're not going to just type it in to the SQL window and then walk away and then leave this job and go to another job and then do it. You're going to get fired or you're not going to get paid, one or the other, because you're going, what did you do? It documents your work. So usually you have what's called a database configuration file. You created the database objects. You used all the SQL commands, which is why you're going to use the SQL Plus window instead of doing it using a GUI method. When you initially establish all this stuff, you're going to put it all in one file. And you actually put it into a script. And I'm going to show you how to run scripts, actually. And then it creates table, creates table, creates table, creates table, populates this, sets this key, grants this user, creates this user account, creates all these privileges, does everything. So you can walk away and then 10 years later come back, hey, you remember that database? It failed. Can you recreate it? Oh, no problem. 2 seconds, run the script. So it goes back in time and redoes everything you did. It's kind of the configuration. Or if you're making a database for someone, you give them this configuration file. And the configuration file is the documentation, essentially, that's going to document all, because you can't see this stuff. It's not like you can print out the database. And you can't see anything. So all you know is it's out there. Well, what's out there? Well, here it is right here. It's in this database creation file that I put together for you. It has all these tables, has all these privileges, has all these users, and everything got granted correctly. New user comes in, you just assign them that role. Oh, okay. Another user comes in, you assign them that role. It's like the configuration of everything. So it's like someone telling you, giving you a map, and here's your map. So you're going to save the map, you're going to throw the map away, or not create the map. So, which is kind of odd. And when people do it all the time. It's called job security. You're the only one that knows what's out there. So what are they going to do? Get rid of you? Yeah. How are they going to get rid of you? They can't. Unless they can force you, and then you can do it backwards, actually. You can go back in and document it after the fact, but it's never really the same, especially, if you want to recreate it, so on the fly. All right, so here's define it after. So instead of putting it with the table field itself, we put it after. Constraint, here's the constraint, here's the primary ID. So composite primary key, some of you might be wondering, how do we create a composite one? We can also do it in the form of a constraint. So constraint name, and it's a primary key, and the primary key is on field 1, field 2. So that's how we get the employee ID with the name of the dependent who's going to be on the health insurance policy. So we take a weak table and a strong table, we connect it together using a composite primary key. We create the composite primary key like this. So you must be defined, has to be defined after the fields that compose the key are defined. You can't do it with the key creation. So when it's a single primary key or a foreign key, the constraint can be contained or created along with the table. So the reason why this option actually exists is because after the fact, you defined all of these fields, and then at the end you're going to say, oh, the constraint here is going to be a primary key, but it's a composite. So it's on student ID and course ID. So whether you like it or not, eventually you're going to have to know this syntax, and you're going to have to use this technique. You can't just put it, oh, here's primary key. Here's like, what if you have a composite? Then you got to put it at the end, and you have to define it as a constraint on the database table. You actually have to specify that it's a foreign key as well as a primary key. So it's done at the table level as well. It can only be defined after the field is defined as a primary key in another table. So the order that you're going to create this documentation that you're going to reuse over and over again, it's going to have all the primaries created first, and then their secondary list of tables is all your foreign tables. So they're going to use the primary keys that you've already created. If you try to put it in a different order, not going to work. So your constraint name references, and the keyword references here says it's a foreign key. Reference is the primary key from that other table. And then we're going to call it primary key from the other table. This is the name that we're giving it. And here's the field name, which is the primary key. So we create the foreign key by saying, hey, in this table over there, we got this primary key, and then we can create it by referencing it. And references creates the foreign. We can actually call it a foreign key and use the foreign key constraint as well. And I'll show you that after lunch when we go to the SQL lecture. So the foreign key constraint here can be defined when the field is declared. So here we have the primary key up here, and then we're going to reference it by faculty. This is the table ID. FID is going to be the faculty ID that's going to be referenced in here. So it says advisor ID. So each one of these students that's being put in here, because we're defining the table my students, the students have a faculty advisor, and we're going to use only faculty that are in the faculty table, and we're going to put a reference of the foreign key of the faculty ID into here, and we're going to put it in as a separate field, and the field's at the end. So when we enter something in, we have to make sure that it's a valid faculty ID that matches something in the faculty table in order to get that row inside of the table. If we don't, we get an error message, and the row won't be put in because the foreign key doesn't match a primary key. elsewhere. We don't have to use the same names. This says advisor ID, even though that's really a faculty ID. So I see a lot of people that actually use the same names as the foreign key, and then it gets confusing. It's like, why do we have faculty ID in here when it's really an advisor? So the student has a faculty ID and a student ID? Huh. So foreign key constraints can also be defined after all of the tables are defined and completed. They can be done at the end, and if you're going to do it at the end, you're going to put it down here. So you have the primary key and the foreign key all established together. This way, when you look at the documentation years down the road, you can easily see all the foreigns and all the primaries because they're always at the end. This is a very small table. If you have like 20 fields in this table, it's going to be big. You got to look all the different lines to see where are the primaries and where are the foreigns in here. If you just see them at the bottom, it's a little bit easier to spot it when you're looking at it 20 years later. So those were key constraints from a table level. We also have value constraints at a column level. This is on the actual column. This is where we get the gender only able to accept an M or an F instead of a Z or something. So on the column level, it restricts the data values that can be inserted. So if you have a telephone number, it has to be 3 with a dash and 4, 3 more with a dash and 4 or something. It has to be the right order. So in general, avoid value constraints because they make the database very inflexible. Because how many times have people tried to put telephone numbers in and you put the little brackets in there, and the brackets get rejected. Doesn't work. Okay. You put the lines in there, lines don't work. Okay. You put this in. It just is impossible to get the data into it. In fact, you've had the frustration probably in earlier applications from web forms you've filled out, or it still happens actually occasionally. I like it when you just select values. Just give me 3 different fields. Area code, prefix, suffix, or give me, put it all, separate it all out. That way I don't have to worry about putting those brackets in and stuff. So we have different types of value constraints. And the interesting thing is those forms I keep talking about, web forms and stuff, is the data we're putting in the database. So it's the acceptance of the data, which is highly linked to the way the data is stored in the database. So if the form is making a mistake, the rows aren't getting into the database correctly. So a lot of people do form checking on it. Well, before you even attempt to connect to the database server to send that data, you're going to check the form. And then you're going to fix the data so it works with the database entry. Otherwise, you're going to get a bunch of SQL errors, and most people have seen this already as well, coming out on your web form. SQL error this, SQL error that. And you're like, what is this world? What's going on with my form? It's usually because the data that you put in there wasn't form checked correctly, or something changed in the database. This happens a lot with shopping cart applications, actually, and because credit card companies are constantly updating their databases and constantly updating their interface to it, and if the data is slightly off, like there's an extra space, there's something wrong with it, it's going to trigger an SQL error at one point, and then you're going to see SQL : bunch of crap that gets printed on the screen. And the user sits there and goes, oh, it didn't work. Yeah, no, it didn't work. All right, types of value constraints here. We can put a check condition. So we can check a condition that restricts the specific value. So if we were going to create that male-female gender designation that's going into this field here called gender, the constraint my students underscore s underscore gender underscore check condition, or CC. The keyword we're using here is check. Check's going to check to make sure that the S gender is equal to M or the S gender is equal to F. So you can't put Z in there. If you put Z or something else outside of an M or an F, it's going to come back with nothing. So it's actually going to come back with an error message and say, sorry, can't insert the rest. It's not going to say sorry, but it's going to say SQL error something or other, insert error, insert something. You can also put not null in there. So not null specifies that the field cannot be null, can't be empty. Actually, a space is not empty. Space is a space, which is an issue for the not null. So the constraint here says that my students underscore student s underscore date of birth underscore n constraint is going to be not null. So people will use NN for constraint. And then you see sometimes this constraint comes back from an error check and says capital N, lowercase a, capital N, not a number. Because it's text. It came out of a database and it was formatted as text. Shows up on the screen and it says NAN on your web form because it's not a number. When I was trying to convert text to number and it couldn't do it. So, and because someone put in 0 and 0 got put into a text field as a space, the 0 comes back out onto the form and says not a number. Still happens. Still happens like a lot. You see that on forms all the time. Types of value constraints. Here as a default you can specify the default value that is inserted automatically so you don't get not a number that comes out of there. As an example, if you're in the state of California, the state would be CA. Here's Wisconsin, WI. So the default, so you specify default when you create the table, and it gives you the default value if one's not given. So the row can be put in correctly, but then everybody's in WI if you don't specify the state. Which is why the web forms are great, because it defaults on data. So you don't fill out anything, you just put your name in there or something and you press submit. The rest of the form is already filled out for you. So it's going to either be used with default values or you're going to get the form itself being filled in, so you have a drop down that defaults to something. Unique is also a table constraint that can be used. It's not a key constraint. It specifies the non-primary key field that must have a unique value. Don't use it as a primary key. Constraint, consultant, email address, unique. That means that you have to have a unique email address in there, which means you can't put the same email address in for all customers. Or for, it's like telephone numbers generally having to be unique as well. Otherwise people put 555, 555, 5555, or 666. Anyway, only one person can do that, and then it's over with. So the SQL Plus window sort of looks like this. It's a command line utility used for entering in all of these commands. And you start it out by having a graphical user interface normally. You just log in. This is the database username. This is the password we gave it a couple lines above. Usually there's a host string. It's the URL where the database is located, where the object is located in the database normally. Not necessarily the case these days. That actual field is out of the GUI, so it's just name and password. And then when you're using the SQL Plus window, all the commands must be terminated with a semicolon, and use a text editor to copy and paste the commands into the window. Nobody's going to sit there and type them all in. You're going to type them in using a notepad or something, and you're going to cut and paste and put them in. Character data is case sensitive and must be in single quotes. So M is a capital M. It's in single quote. It is case sensitive. Sarah with a capital, with a quotes around it. When you exit the SQL Plus window, you type in exit. It's very much similar to a terminal prompt on a Windows system, or excuse me, on a Unix system. And you click in close button on the SQL Plus window to close the window. So a lot of people log in and then they don't log out. They just close the window. So the window itself actually closes and logs out automatically. So if you install Oracle on your system and you just log out, it'll just log you out if you close the window. It's user friendly these days. We also have some help that's available in the resources that's installed on the system, the Oracle Technology Network. Now it's on the Sun site, but this URL is very similar actually. So this is probably one of my most favorite Oracle-specific SQL Plus window commands. It's called describe. Describe is nice because you create all this stuff. You put all the stuff in here, you created all these tables, and now you're like sitting at this blank prompt. Now what do I do? I want to run a query, but what am I running it on? So you can describe a table. So you can say describe space table name. Here we just describe my students. And what do we got? The ID, the name, the date of birth. What we have is a table description. And the description is everything that was included in the script that we created. So we have the type, and we have the not null status, let's say for example of ID because it's primary, that was given to us automatically. So the describe command just describes what's in the table structure because we can't visually see it. But it's there, created it. We also have this thing called the data dictionary. So the Oracle data dictionary is held by the system. It's in the system user schema. So if you type in, you go to the system object. Actually, the admin is called system as well. You log in as system. You view the objects in the system object. And the objects you're going to get back are going to be tables and views and things. You'll see a table of users, a table called dual, that's going to have all of the system date and system information, the install date, what is our current date, how many users are there, a bunch of information is out of dual actually. You can query the tables. So you can log in and query how many users do I have? How many of them are logged in right now? What are my sequences? I'll talk about sequences later on. What are, how many tables do I have? Well, who owns what? All the information is actually stored in system. So it contains the tables that describe the database structure. Automatically updated as users create and modify tables, which is interesting. So the system doesn't have to do anything. All the users that are logged in, they're automatically updating the system tables. So they have access to update, but they don't have access to view. So users can't view the system table. Can't be updated directly, it has to be updated through user activities that's being performed. Contains the views that all that allow users to retrieve information about the database structure, but they can't change the database structure. So the view mechanism is used on all of the system tables. So when you're another user and you query dual, as an example, to get the system date, or to get the current time, or get something about the system, the version number or something, you're actually querying a view. So that's the one account that has the most views in it. All of the system tables have views that are associated with the system table. And you're querying the view, which means you can see the information, you just can't change it. So data dictionary views. The view represents the data in different formats, depending upon the privileges of the user. So we can create a view, depending upon your privilege, you have access to certain fields. It's like you in the HR department. You can't view all of the performance reviews normally that are in the table, or you can't view certain information that's in there, certain notes that the administration has said about you and stuff like that. You can only view your data, and you can only view certain things about your data. So it represents different views. So we have the user, shows all the objects belonging to the current user. All shows all the objects belonging to the current user as well as anybody else, any other user who has privileges to manipulate your objects. So you're the HR object, and you're a user with a role, and you have privileges to the HR object. You can grant that privilege to other users who belong to other objects. And when you do that, they get different privilege levels for their views on the system tables depending upon who they are and what role they fit into. So all is applying to them, and it's applying the same view that the user gets from a user, but to other objects that don't belong, other users, that don't belong to the same object. Believe it or not, there's a dot notation. So we have, as an example, if I have a user called bhacker, and I was created inside of the HR object, I have hr.bhacker. I can also be involved with other objects. So I can have access to marketing.bhacker, and I can actually be a separate user in the marketing department. So there can be two bhackers, one in the HR department, one in the marketing department. Or I can get privileges to the marketing object, even though I'm in the HR object. So it just kind of makes it more functional because we don't have to keep recreating users and giving access to everything. We just grant privileges to use different objects. Depending upon what my job title is and what I'm supposed to be doing, I can have all of these different object access, which is what you get into when you start looking at how to configure the privileges. So the DBA allows the users with DBA privileges to view the objects of all of the different database users as well. So we can grant a privilege called DBA, which is not admin or system. It's different. So it's a DBA, which allows them to grant and revoke privileges at certain levels of the privilege hierarchy. So Oracle probably has one of the most sophisticated privilege and security system available, which is why people like it actually. Querying the data dictionary. So we can select field 1 and field 2 from privilege view name. So what do we have here? Select table name from user tables. These are actually the names of these. So we have a table name field that's inside of user tables. So we can query the user table. We can get, well, we have category, client, color, and consultant. Or we can select it from all tables. So we have user tables, all underscore tables, and DBA tables. So this is all the tables that the DBA has access to. This is all of the tables, and this is just the one in the user tables. So we could essentially create a pretty sophisticated hierarchy of privileges that are by object and assign users to different objects. So that's why I said originally it's kind of like Unix, or Linux actually. The level of control is fairly sophisticated. So the summary of the Oracle Data Dictionary views, we can view objects, which are all the database objects, tables, indexes, views, sequences, indexes, and sequences, and views. So it's probably not a bad idea to understand the differences between them, only because the terminology is used and people often have a tendency to mix them up. An index, you can create an index on a table yourself, or you can let the system do it for you automatically. If the system does it for you automatically, it takes in each one of the tables its primary key, indexes the table on the primary key. So the table indexes are created to improve the query performance. You never touch, as a user, you never touch the indexes. Indexes are for query processing and optimization. You can reset the index, you can update the indexes, or you can create your own index. So if you don't like the primary key being indexed, you can index the table on the foreign key, which a lot of people do, because then they can search on the foreign and they can search on the primary at the same table. The more indexes you create, the slower the system runs. If you have a table and it has 5 indexes on it, great. You've just now, it's kind of like a weight. No indexes at all, it's going to be slow. Add an index, oh, it's faster. Add another index, okay. A little bit faster. Okay, add another index. Now we've slowed it down because you got to query. It's got to go through every single one of those indexes before it returns the results. And it's not in the indexes. You're adding more to the search space. 1 index is good. 5 index is not good. So 1 index is okay. So use indexes sparingly. Here's another problem. You index the table. Then you start adding data to the table. Every single time you add an item to the table, it has to update the index. So normally, hold on one second, let me do indexes one more time here. So you indexed a table. You want to index the table after you populate it with data. Then the table runs faster. If you index it before you populate it with table data, every single one of your updates to that table and your inserts makes it run slower. Because you got to update the table, update the index, update the table, update the index. So you don't want an index on it when you're populating the table. So normally people selectively turn off the indexes, update all the tables, get all the tables ready to go. Let's say you're Barnes & Noble and you have a whole entire table full of publishers and books, and you're going to populate it. So pull off the index, populate the table, re-index it. Indexing takes about 10-15 minutes. Index gets recreated. Searching on it is much faster. So it's kind of the thing that the DBA does, is going to select when you're going to do the indexes, and that's what indexes means. A view, a database view, is not viewing the table. It's viewing an artificial view of the table with restrictions added to it. You can update a view as long as the view is only based on one table. If the view is based on multiple tables, you can't update it. So you're not going to really use a view for updating, because a view is a projection that's done, a query that's done on a table already. Runs slower. So you create a view for query but not update. Because the update on a view is going to take too long. So the user logs into wellsfargo.com and pulls up their information. They're looking at a view. Are you allowed to update? Not very much. Most people just view stuff. So think of view just like the word view. You're viewing it. You're not updating it. You're not changing the data. You're just viewing the data. Let's just see my cell phone bill. You're looking at a view. You can't update that cell phone bill. So, sequences are numbering schemes. They are not indexes. This is where most people get wrong, and I know this because of multiple choice exams I've given in the past. People think an index and a sequence are the same thing. A sequence is a numbering system. So a classic example of a sequence is what you get with your checking accounts. Every one of your checks is sequenced as a check number. We can take the check number, which is a form of a sequence, create a sequence that represents check numbers, or ATM transaction numbers, or withdrawals, or anything you want to keep track of in a sequence of numbers. Even student IDs can be a sequence. Put them in a global sequence table. When people do transactions on the ATM machine, going back to Wells Fargo, every single person who comes in to the ATM is getting a new sequence number. So from the morning to the nighttime per day, the ATM knows transaction number 1, transaction number 2, transaction number 3, transaction number 4, number 5, number 6, all in a sequence that's held in a system table that's updated per user, per activity, for anything that goes on with that ATM. It's a global numbering system that works with all users. So your number that comes back on your sequence, if you've ever looked at your receipts, there's a sequence number on there because it needs to know what number you were in the system. So the sequence is created automatically and generates surrogate key values that are used with multiple different tables. So you have one sequence. You call it my numbering scheme, my ATM receipt numbers, and then all of the tables that are using it can go and query, what's the sequence? Give me the next. Give me the next. Give me the next. You're automatically incrementing a global list of numbers called a sequence and using it to update different fields and different records for different users in different tables at different locations. Wells Fargo can keep track of sequence number 5. What's sequence number 5? Look it up and it says, oh, it was done in Campbell, California. Sequence number 6, oh, that was done in Florida. Sequence number 7, oh, that was done in Colorado. Sequence number 8, that was done, and then this is the location that's associated with the transaction. It can keep track of a global list of transactions per day, per month, per year, all together. That's the value of the sequence. Don't put a sequence in a table unless you need one. It's not a surrogate key. It's meant for global organization. As a user, you have sequences with your checks. You're not supposed to repeat. You're not supposed to go back and use a check number that was like from 2 years ago. You never repeat those numbers because I can't tell. Oh, check number 5 was for $10. Oh, you meant check number 5, that was for $20. Oh, check number 5, you can't reuse the number. It's like Social Security numbers are a sequence. Excellent example. Every single person in the United States has a Social Security number. You're supposed to have one if you're a citizen. It's a global sequence that's used, that the government put together. There's no duplicates. In fact, you can figure out who that person was after the person has died. And then they know because some people illegally use Social Security numbers. They look it up and they go, oh, that was from this guy who died back in 1907. Because they buy them on the market. They don't know that these numbers are in the sequence kind of thing. So people buy fakes. Usually it's people that come into the country illegally. They'll buy fake Social Security numbers on the street. They sell them at flea markets and stuff too, And then you use it. Actually, there's a lot of illegal aliens that have been paying taxes with fake they're not fake, they're real Social Security numbers from people who have been deceased for 20 or 30 years. And all of a sudden, this person is back up again and they're paying taxes. It's great. Unfortunately, when you go to get those taxes back, you pay into taxes so you can get Social Security insurance for, retirement and health benefits and stuff. You can pay in as much as you want, but you're dead. If you're using somebody's 30-year-old, they died 30 years ago, but you're never going to get money out of them. They're going to come back and say, oh, sorry, you're deceased. Oh, but you're still paying in on that. I don't know why people do that, seriously. It's because you can't get a job unless you show that you have a Social Security number. So the illegal aliens can't work unless they get somebody's 30-year-old, somebody who died 30 years ago or 20 years ago, recycled number that comes through that's good. It's good because nobody else is trying to collect from it. So it works. But the government will take your money no problem. They're just never going to give it back to you. Which is kind of ironic. So then there was, for a while, there was an initiative that said, okay, we can give you a social security number even though you're an illegal alien. Because they wanted these people at least to get their money back. And then the politicians went, well, why are we going to give illegal aliens valid social security numbers? So that stopped. So anyway, a lot of controversy with that. But now hopefully you'll remember what a sequence is. It's not an index on a table. It's not a surrogate key in a table. It's a value that's held by the database that's used over and over again, and it's attached to some meaning, but it's never usually repeated. It's a sequence, so it's kept track of and it's logged by the system tables. Okay, that was a sequence created automatically. Generates a surrogate key value when one doesn't exist. Normally we're not born. We have birth dates, but we don't have social security numbers, so it's a surrogate value for us. So, all right, these are other things I was discussing that are in the data dictionary. We can create our own sequences, and we'll see how to do that after lunch when we look at the SQL queries. So, we can also modify tables. Modifying tables, we have unrestricted access and actions I can do. Not such a good idea either. Once you create everything, leave it alone. Because you have a bunch of data that you populated, you indexed it, and everything's ready to go. And then you add another field to the table, another column, and all of the existing data doesn't have a value for that. So it's going to say unknown, 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 unknown. A bunch of garbage in there. So you want to make sure all the and then you can't enforce integrity constraints. Can't be null. How are you going to do that? It's null for like 2,000 records that's already in the table. So you can also, however, rename tables. You can add new columns to tables. You can increase the column sizes. You can drop columns, drop constraints. You can do anything you want to it. Whether it's advisable is a different story, but you can do it. In terms of modifying those tables, we can restrict the access. So, dropping tables, only allowed if the table does not contain any fields that are referenced as foreign keys or if the foreign key constraints are dropped. So we don't make sure we can put some integrity inside of the structure of this so that if we're accessing something as a foreign key and we're using it in another table, we can't get rid of the table. Dropping actually means not necessarily get rid of it, it just removes all the information out of the table. Truncating it removes the information, gets rid of the table, doesn't keep a backup of anything. Dropping actually does to a certain point if you put on a manual way of kind of like resetting the table. Doesn't really hold any rollback information. Or dropping holds rollback. You can restore a drop table, but you can't do it on a truncate. So, and I'll talk about table spaces and memory as we go through the probably in the session 2 of this course. Changing a column's data specification only allowed if the existing data is compatible with the new data specification. If it's a date, you probably could change it to text. If it's text, you can't change it to a date. It doesn't work. It's not going to be compatible. Decreasing the column size, you're going to truncate only allowed if the column does not contain any data. If there's data in there, it's not going to truncate. You're going to remove data? Not going to work. You can add a constraint only if allowed if existing data meets the constraint, which means you got to clean up the data in order to allow the constraints. And then you get issues. So, well, it's like how we can't necessarily make it so that students aren't in the student database twice with 2 student IDs. We would have to remove student records in order to make that happen, which we can't do. So we will forever have multiple students with multiple student IDs in the database because we can't add that constraint because we can't clean up the data without removing students. When you don't want to remove a student, we're going to lose their records. So, but we can put in rules to require a primary key for certain information. Come up with surrogates for those people who are duplicates. So, altering tables, adding a new field. Not advisable either, but we could alter table, name of the table, add this field. Okay, we added a new column to the table, so all the other existing data doesn't have this column information. So, In terms of altering tables, we can also modify it. So we can say modify an existing field, alter table, instead of adding a new field, modify this field, modify it so it's now bigger. Instead of 5, it's now 10 characters, or 30, now it's down to 10. In terms of, and it says table altered. And you get table altered here when you add. So this one's adding a start date, which is going to be, it's a date format. And then deleting, so we can add, update, delete different fields that we've already created in the table. Oracle's pretty flexible. You can almost do anything you want with it. Drop a column, dropping deletes it. So the word drop is used a lot for dropping tables, dropping columns, drop deletes. We can actually delete the entire table by dropping the table. So the syntax to delete a table: if no table fields are referenced as foreign keys, this works. If not, we have what's called a cascading delete or drop that occurs, and if the cascade fails, it's still being used, it won't get rid of it. So there's integrity and constraints being put on the table structure given your foreign and primary keys as well. So a lot of people who don't know how to do this will not specify foreign and primary keys because it makes it more difficult to get rid of the table. But then you're just introducing more problems, because you're going to put something in as unique, great, but there's no key, so there's no referential integrity to be enforced, which means you can drop and get rid of anything you want, which opens up the door to make it easier to drop tables. However, you just created a really bad set of data with bad information. So people will alter the table, remove the key so they can drop the table, another table. And it's like, well, you just removed something that had referential integrity. You took off the referential integrity so you could delete it to ruin the integrity, and now you can't put it back on. So then they run into situations where you can't stick the reference back on there because the table doesn't meet all the requirements because somebody changed it. So if you ever do any database consulting, these are the things you'll run into all the time. Tables with no keys, tables where they've used unique instead of keys, tables with multiple keys, multiple indexes, tables that they've removed the keys, they've dropped related tables, and then they put the keys back, and they can't put the keys back on. And then all these weird situations that occur because people have done things that were not logical in terms of the table structure and the referential integrity. So syntax to delete a table and its constraints is used here, cascade the constraints. That's dangerous because you're going to delete data out of other tables as well. So you're deleting one table and you're going to update and change and delete data out of 5 or 6 different other tables. And it works, but then you go back and look at it and go, oh, maybe I didn't want to do that. I've deleted all the student IDs now out of the entire system. Oh. Nobody's got a student ID anymore. Oh, okay. How are we going to get at the records? Can't. So, might cause a problem. But the syntax exists and you can do it. So, not to scare you, but these are some of the things that you run into, especially if you do any consulting work. You're lucky, going back to what I said yesterday, if you can just go in and design it from scratch to begin with and remove everything that's there. It's like when you go in to fix somebody's source code. Sometimes I wish I could just rewrite it myself, because if I rewrote it myself, I'd write it with a little bit more integrity, a little bit more better structure. Then if you try to fix somebody's code that's broken, it takes you twice as long to fix the broken code as it would if you just rewrote it from scratch yourself, created it yourself. Unfortunately, what ends up happening is people have these databases that have been in operation for years and years, and it's populated with so much data, like ITU as an example. Tons of student data. How are you going to fix the multiple student IDs? You can't. So they're just happy leaving it alone. So how can you fix it as a student? You can't. How can you fix an administration point? You can't. What are you going to do? Drop the table? Take the keys out? Change the integrity of the keys? You can't do it. But if you rewrite it from scratch, how are you going to get all the old data into the new data when it doesn't follow the right format? That's also going to be a problem too. So the longer the problem exists, the more workarounds people put into it, the more the database decays in general, and more the logical structure is broken down. which is actually the philosophy that software engineering follows. The longer you maintain source code, maintain a database, the worse condition it gets into, and you get what's called decay. The entire system will decay and wear out and not be fixable eventually. And then you just replace it with a brand new one at that point. So, all right, we're going to take a lunch break, and then we're going to study SQL from the ground up after lunch. We need a break before we do that one. So let me end this video.